So the next part of properties. Now, before we go into the other part of the properties, okay, we have the temperature first. Now, temperature and the zeroth law of thermodynamics. Now, zeroth law of thermodynamics, in other words, you can call it as thermal equilibrium, a thermal equilibrium process, zeroth law. So the zeroth law of thermodynamics, okay, what it is, if two bodies are in thermal equilibrium with a third body, they are also in thermal equilibrium with each other. So in other words, let's say for example, you have one object, okay, and then you have another object, okay, which both is under thermal equilibrium. So now what happens is, if this object A and object B is brought into contact with the third object, so object A and object C will comes to a thermal equilibrium, and then object C and object B also will comes under thermal equilibrium. So once all the A, B, and C, they are in contact, they will finally reach, okay, a state of thermal equilibrium. For example, you have object A, object B, you have person A, you have Yach, and you have Yap. They are actually practicing this social distancing, but the temperature usually is different. Okay, the temperature, body temperature of Yap and body temperature of Yach is different. Let's say, for example. So if let's say, for example, you have a third person, let's say you have a gun, okay, come into contact with both of them and holding the, that means holding the both of them on their shoulders. So what happened is, if let's say, for example, all the three person now reaches the same temperature, then we say they are under thermal equilibrium. And that practices the zeroth law of thermodynamics. Okay. Now, in other words, it refers to thermal equilibrium. Okay, don't type anything, please. Now, by replacing the third body with a thermometer, if you have a thermometer placed in between the both objects, the zeroth law can be restated as two bodies are in thermal equilibrium if both have the same temperature reading, even if they are not in contact, okay? This, for example, is iron and copper, okay? So when they reach, okay, a same temperature between the iron and copper, okay, they are said to be under thermal equilibrium, okay, that obeys the zeroth law of thermodynamics. Okay, two bodies reaching thermal equilibrium after being brought into contact in an isolated or enclosure system. Okay, that is an isolated system, okay. Now, what are the temperature scales? Now, temperature scales, temperature is usually measured in terms of degrees C, in degrees Fahrenheit, and in Kelvin. So for SI units, we only refers to degrees C and Kelvin, okay? Now, all temperature scales are based on some easily reproducible states such as freezing and boiling points. The freezing points and the boiling points. All temperature scales take these two as the reference, that is the freezing and the boiling. So for water, okay, the freezing point or ice point is 0 degrees C. Everyone knows that, right? And for steam point or the boiling point is at 100 degrees C. Okay. So ice point is a mixture of ice and water that is in equilibrium with air saturated with vapor at 1 atmosphere. So you are referring to, and at atmospheric pressure, 1 atmospheric. So that is basically at 1 atmospheric ice at temperature 0 degrees C. So at different pressure, this ice point will be different. So you have to be very careful in defining the ice points, which is 0 degrees C. So you must always say it is at 1 atmospheric. Then the ice point or the temperature should be 0 degrees C. As when you refer to a different temperature, then this value here might be different. So that is why this 1 atmospheric here is very important. Okay. So at 1 atmospheric, the ice point is at 0 degrees C. The boiling point is at 100 degrees C. Okay. So also referring to 1 atmospheric, you see the notes here. Okay. And then the boiling temperature or the steam point will be at 100 degrees C. Now, Celsius scale for SI unit system, okay? Celsius scale and Kelvin, okay? Kelvin is called absolute scale. So the reference temperature in the original Kelvin scale was ice point 273. So 273.15 Kelvin. So for temperature degree C to Kelvin, okay, temperature degree C is 0 degrees C. For ice point, the temperature is 0 degrees C, okay? But if you want to get to Kelvin, so you take 0 degrees C plus 273. We always, okay, ignore the 0.15. We can plus 273 to 0 degrees C to convert it to Kelvin, that is 273, okay? So for boiling, then you have to take 100 plus 273. Now the reference point was changed to a much more precisely reproducible point, the triple point of water, okay, which all three phases of water coexist in equilibrium, which is assigned to the value of 273.16 or 15 Kelvin. Okay, so that is called the triple point. But then we don't usually refer to triple point. Pressure, that's temperature, and now this pressure. Now remember temperature, okay, if let's say for example you want to measure the temperature of any molecules or particles which is in Kelvin, remember if you want to convert from degree C to Kelvin, you have to always add it with 273. From Kelvin to degree C, you always have to minus 273. Okay. So pressure, definition of pressure is a normal force exerted by a fluid per unit area. So that is force per unit area. Force per unit area will give you pressure. That is in Newton per meter square. Newton per meter square. We know that 1 Newton per meter square is 1 Pascal. Okay, 1 Newton per meter square is equivalent to 1 Pascal. So 1 bar is 10 power 5 Pascal. Okay, 10 power 5 Pascal. That is also 10 to the power of 5 Newton per meter square. 1 bar is equivalent to 10 to the power of 5 Pascal or 10 to the power of 5 Newton per meter square. For atmospheric pressure, 1 atmospheric always refers to 101.325 Pascal or 101.325 kPa. That is 1 atmospheric. That is 1 atmospheric. 101.325 kPa or kilonewton per meter square. Or that is also equivalent to 1.01325 bar. That is the atmospheric pressure. So when you say 1 atmospheric, that means you are referring to 1.01325 bar. Okay, so this is diagram. This diagram here shows you the pressure measuring device. Okay, the pressure measuring device, the gauge. Okay, the pressure gauges. Now we are not going in depth. Okay, we are not going in depth. We are just brushing through the whole thing. Now, what's absolute pressure? The actual pressure is at a given position. It is measured relatively, okay, to absolute vacuum. So absolute zero pressure. Now, usually absolute pressure can be taken as the atmospheric pressure, absolute pressure can be taken as the atmospheric pressure plus the gauge pressure. Okay, so what is gauge pressure? The difference between the absolute pressure and the local atmospheric pressure. Most pressure measuring devices are calibrated to read zero in the atmosphere. Remember this point here. Most pressure measuring devices are calibrated to read zero in the atmosphere, and so they indicate gauge pressure. So any reading from the pressure gauges, okay, any reading from the pressure gauges that you took will be referring to gauge pressure. Okay, vacuum pressure, pressure that is below atmospheric pressure. Atmospheric pressure is measured by a device called a barometer. Thus, the atmospheric pressure is often referred to as barometric pressure. That is atmospheric pressure. So if you take gauge pressure, this gauge pressure here, plus the atmospheric pressure, you have what we call absolute pressure. Okay, absolute pressure means gauge pressure plus atmospheric pressure. Any pressures that is below atmospheric is usually known as vacuum pressures. Okay. So pressures usually is measured with respect to vertical distance. Okay, vertical distance, not horizontal distance. Yeah. A frequently used pressure unit in the standard atmosphere is defined as pressure produced by a column of mercury that is also equivalent to 760 mm height mercury. So 760 mm usually refers to at 0 degrees C. So 760 mm is your atmospheric pressure. 760 mm is your atmospheric pressure. So if you want to convert this 760 mm to Newton per meter square or to Pascal, you have to first convert this 760 to 0.76 meter. 0.76 meter, that is converting the mm to meter first, then times with the gravity, okay, that is 9.81, okay, or 9.807 here given, or 9.81 meter per second square, okay, and then multiply by the density of this, okay. The density of mercury is 13,600 kg meter cube per meter cube. So if you take density times gravity times 0.76, that will give you the pressure, the atmospheric pressure in Pascal or in Newton per meter square. Remember, density rho g h, okay, or z. In this case here, we use the symbol z for height. So rho g z. So rho is the density of the substance. G is the standard gravitational attraction, 9.81, and then Z to be the depth, okay, or the height of the column of the substance. Okay, for example, if you take mercury, so it is 0.76 meter times gravity 9.81, then times with the density of mercury of 13,600 kg per meter cube, you will get the atmospheric pressure of roughly around 101.325. Okay, 101.325 kPa. Follow? So this is the diagram, okay, showing you, okay, that the absolute pressure actually is equals to the atmospheric plus gauge pressure. Okay, the absolute pressure is atmospheric pressure plus gauge pressure. Okay, so vacuum pressure is any pressure that is below the atmospheric condition or below the atmospheric pressure. Voilà. So for absolute pressure, in this case, you have to take atmospheric pressure minus vacuum pressure in order to find absolute if you are referring to a vacuum pressure. But then usually we take absolute pressure as gauge pressure plus atmospheric pressure. Okay, that's for pressure. Then we have the internal energy. Okay, internal energy usually is measured in kilojoules per kg or kilojoules. Okay, it depends on whether it is the absolute internal energy or the specific internal energy. So absolute internal energy usually is denoted by the symbol uppercase letter U, and the unit measurement is kilojoules or joules. Okay, kilojoules or joules. If let's say, for example, it refers to specific internal energy, then you use a lowercase letter U, and then the units will be in joules per kg or kilojoules per kg. Okay, and what is internal energy? Internal energy is actually the sum of all microscopic. What is microscopic? Okay, microscopic is when we are looking at the state of molecular levels. Okay, the molecular levels. Okay, now, so that is the sum of all the microscopic forms of energy, or defined as the degree of molecular activities. Now, remember this internal energy here, okay, has a function to absolute temperature. Has a function to absolute temperature. So internal energy will increase, or the degree of molecular activities increases when there is an increase in absolute temperature. That means when you are taking temperature in Kelvin form, okay, in Kelvin form. So the degree of molecular activities will increase when the absolute temperature increases. The degree of molecular activities will decrease when the absolute temperature decreases. Okay, when there is no change in absolute temperature, there will be no change in internal energy. So internal energy has a very close relationship with absolute temperature. So according to Joule's law, what we have said just now is Joule's law. Joule's law says that, okay, internal energy will increase when absolute temperature increases. Internal energy will decrease when the absolute temperature decreases. And when the absolute temperature remains constant, then the changes in internal energy will be zero. Okay, hold on for a second. Okay, so I will put this in for you. Hold on for a second. Actually, our recording all are quite lengthy, because it's based on class. Okay, it is not a full only explanation. Okay, so I have to do the explanation. Okay, and so on. Okay. There's my triangle. Go on. Sorry, they will take you some time of yours. Where is it? Okay. Everyone still here?
Yes, sir. Stop texting lah. They cannot see. Sir cannot see lah.
You cannot see me?
No, I can see lah, but they cannot see. I mean, you cannot
Oh,
see.
I cannot see you all.
Yeah, talk lah, dogs.
Yeah, don't say those words, yeah, because I
Oh,
am
recording.
doing recording. I'm doing recording, yeah.
Okay.
Okay, so we're back to this. So that's internal energy. So from here you can see, okay, that when the internal energy increase, when the absolute temperature increase. So when the absolute temperature decreases, then the internal energy will decrease. When there is no change in absolute temperature, that is zero, there will be no change in absolute internal energy. So that is based on Joule's law. Remember this temperature here, that is the absolute temperature, that is in Kelvin. Okay, so that gives you a relationship between the internal energy and the absolute temperature. Okay, stop typing, stop typing. Now, some physical insight of in the internal energy. Now, what are internal energies in more in depth? Okay, other than okay defining it as the sum of all microscopic forms of energy and the degree of molecular activities and so on. So they can be categorized as sensible energy, the portion of internal energy of a system associated with the kinetic energies of molecules. That is associated with the kinetic energies of molecules. We call it as sensible energy. Then latent energy is the internal energy that associated with the phase of the system. So that provides a phase changes. Let's say, for example, from ice to water and so on. That is called the latent energy. Then chemical energy is the internal energy that associated with the atomic bonds in a molecule. Okay, that means the intermolecular bonding, okay, which tends to bind, okay, the molecules together. Okay, so that is related to chemical energy. So internal energy, when you sum up all these energies here, actually will give you what we call internal energy. If you sum up all these energies here, will give you what we call internal energy. Okay, so and then you have the nuclear energy as well. So you have this thermal, when you refer to thermal, okay, form of internal energy that consists of sensible and latent. That means these two. When you are referring to the internal, then you have sensible plus latent plus chemical plus nuclear. That means when you refer to internal energy, that means it constitutes, that means it is made up of all these energies together. Okay? So these are the form of, okay, these are sensible energies. Those are the kinetic energies. Yeah, these are the kinetic energies. Both includes motion. One is translation, moving in straight line. The second one is rotation. This is vibration. Okay, so this will give you what we call, okay, the sensible energy. Okay, so that is all about internal energy in general. So then you have enthalpy. Enthalpy is also a properties of thermodynamics. Now, what's the definition of enthalpy? So in thermodynamics, enthalpy is a thermodynamics property which is equivalent to the total heat content of a system, the total heat content of a system. It is equals to the internal energy of the system plus the product of pressure and volume. So enthalpy basically is the sum of internal energy with the product of pressure and volume. So we use uppercase letter H here to represent absolute enthalpy, which is measured in kilojoules. If you refer to specific enthalpy, then we have to use a lowercase letter h, which is in kilojoules per kg. So this uppercase letter h here, that is absolute, should be in kilojoules. If specific, that is lowercase letter h or the small h, then that will be referring to kilojoules per kg. And then enthalpy is actually given as U plus PV. Okay, so when you look at this uppercase letter, uppercase letter, uppercase letter, so that means this is absolute enthalpy, absolute internal energy, and this is absolute volume. That means only in meter cube. So we'll give you kilojoules. If you have H equals to U plus PV, this is the specific enthalpy, specific internal energy, specific volume, then it will give you kilojoules per kg for your specific enthalpy. Okay, so that's for enthalpy. So the next one is the entropy. So entropy is actually defined, okay, as dq over t. In general, it's defined as dq over t. So in other words, from here you can see, okay, heat is actually a path functions of the entropy and temperature. So entropy is what? Entropy is defined as the quantitative measures of disorderness or randomness in a system. The disorderness and randomness is in a system. That means, let's say, for example, you refers to solid. Solid, usually the molecules, they are measured in order. But then when you refer to gases, the molecules, they are not arranged in order. They move at random position. That means they move randomly and disorderly for entropies of gases. Okay, so that is why entropy for gases usually is very high as compared to solid, where the molecules, they are arranged in order. So that is, in other words, what is actually the entropy. Okay, so you can define entropy as this, but then to explain entropy, so it can be explained as the quantitative measure of disorderness or randomness in a system, the disorderness and randomness of the molecules or the particles within the system. Okay, so the concept of thermodynamics, which deals with the transfer of heat energy within the system. Okay, within the system. So that's why entropy is very important. Remember, okay, entropy will increase when you supply heat to a system. Entropy will increase when you supply heat to a system. Entropy will decrease when you cool a system. That means when there is a heat rejection from a system, entropy will decrease. When you supply heat to a system, entropy will increase. When you remove heat from a system, the entropy will decrease. When you don't supply or when you don't remove, entropy will not change because the heat is not changing. Okay, the heat transfer, there is no heat transfer. Okay, so there will be no change in entropy. So when there is no change in entropy, usually the process we call isentropic. Isentropic refers to constant entropy. The adiabatic refers to a well-insulated system. A well-insulated system or a well-lagged system, L-A-G-G-E-D. Okay, so when a system is isolated or is lagged properly, okay, perfectly, then there will be no heat flow across the boundary. So there will be no heat transfer or no heat flow. So Q will be zero. So under such circumstances, the change of entropy also will be equals to zero. So that is why we say adiabatic is actually the same as isentropic. So if you want to refer to constant entropy, you can always use the word isentropic or adiabatic. So is constant entropy where the net change in entropy or the changes in entropy is equal to 0. When the Q is 0, Q represents heat transfer. So Q represents equals to 0. So some entropy is generated or created during a reversible process. Okay? During an irreversible process, you all should know what is the difference between reversible and irreversible process. And this generation is due to entirely to the presence of irreversibilities. So when a process becomes irreversible, there will be some entropy generation. There will be some certain amount of entropy generated. Okay, that also will cause an increase in entropy sometimes. Entropy is an extensive property of a system. Okay, so it's usually given as kilojoules per kg Kelvin. Okay, or kilojoules per Kelvin. Entropy is measured in kilojoules per Kelvin or kilojoules per kg Kelvin. It depends on whether you refer to absolute entropy or specific entropy. So entropy generated will be greater than 0. Entropy generated will be greater than 0 for any irreversible process. And then entropy generated will be equals to 0 for any reversible process. Entropy generated will be less than 0 for any impossible process. That means it's impossible. Okay, entropy is a non-conserved property, and there is no such thing as conservation of entropy principle. There is no such thing as conservation of entropy principle. Yes, there is conservation of mass principle. There is conservation of energy principle. There is nothing known as conservation of entropy principle. Now, the performance of engineering system is degraded by the presence of irreversibilities. The performance of any engineering devices, okay, will decrease, okay, when there is a presence of irreversibilities and entropy generation. Okay, and entropy generation. This is very important, yeah. It's the measures of the magnitudes of the irreversibilities, where entropy generation is the measures of magnitudes of the irreversibilities during that process. It is also used to establish criteria for the performance of engineering devices. Okay, so remember, entropy is the lowest for solid and is the highest for gas. Entropy is the lowest for solid and highest for gas phase. Okay, that's all for the second part. Okay, everyone still here?
Yes.
Judge, please, when I'm doing recording, please, you can say anything but not vulgar words.
I see.